So, welcome back to Atomic Theory and Structure, and we are going to be forging ahead into a quick review, very quick review of electromagnetic radiation, and then finally moving into our models of our structure of the atom. Now, we did this in pre-AP. You've seen much of this in physics, and we need to understand electromagnetic radiation for two reasons mainly. One, it ended up that there is a wave nature to matter that was exploited by Schrodinger among others, and that the mathematics of that, the mathematics of waves, was used to help us determine at least a region in space where there's a 90% probability of finding an electron. So that's one of them. And the second is, it is quite common to use the interaction of electromagnetic radiation with matter to study matter and the structure and function of matter. So this is very, very valuable math. This shows you a wave. It gives you the wavelength. Our wavelengths are typically measured in meters, nanometers, and sometimes centimeters and angstroms. An angstrom is 10 to the minus 10th meters. It gives us the speed of light. Here's the speed of light in meters. It's also good to know the speed of light in nanometers. Sorry about that. This Mimeo, when I bring in my PowerPoint, it didn't quite work. And so 10 to the 17th would give us nanometers, which is quite handy because that's the region of light for visible, and it's good to be able to move back and forth without having to convert to meters all the time. Now, our formula for frequency and wavelength is given here. The speed of light is our wavelength times our frequency. Now, bear in mind that physics tends to use an F for frequency, and we use the Greek letter nu. If you had to handwrite it, I'd probably do it something like that. The Greek letter word nu. Now, the energy, and it's very important that you see that this is the energy per one photon of light. It's not for a mole of photons, and we'll do that conversion on another page. I'll show you one. But that's for one photon of light, and it doesn't really explicitly say that. It'll give the energy in joules, but it'd be nice if they gave it in joules per photon. Just like if I gave you the mass of an atom, I would give it to you in grams, and I don't say grams per atom. And so that would be really nice. It would help in some of the mathematics, but it's not done. That energy is Planck's constant. He was one of our dead guys, times the frequency. So what you want to take away here is if we increase our frequency, we increase our energy of the light. So increased frequency is increased energy of light. Now, if I solved this for frequency, if I solved this for my frequency term and then substituted, I would get energy in terms of my wavelength. And that's Planck's constant. That will always be given. It's given right here. And the speed of light. And what you need to do for units here is make sure that your units in the speed of light match your wavelength units. So we want to match units, meters to meters, nanometers to nanometers. Now, the speed of light in meters will be given to you. So this should be meters per second for that speed of light. That's given to you. The one in nanometers is one you would have to memorize if you like to use it. Now, what this shows is that as I increase my wavelength, making that a longer wavelength, since its length I don't like to talk about high and low, but a longer wavelength, that means we're talking about a lower energy in terms of the electromagnetic radiation. Now, big assumption here, you need to be able to use these. So you need to be able to do the plug and chug and substitution and use these three formulas. You will have them in homework, but I'm not going to go over any in class. Instead, we're going to move right into atomic structure. So now, we're going to come back to Bohr now. Bohr, remember, helped us out by providing those quantized energy levels, and we're going to look at a diagram of that. Max Planck, in terms of getting into the quantum mechanical structure of an atom, came up with the particle nature of a wave. So just like we're going to be talking about the wave nature of a particle, that was Schrodinger, wave nature, and de Broglie, by the way, wave nature of a particle, Planck said, hey, instead of thinking of a wave as a continuous movement, can we think of it as little particles of energy that we just saw that we call a photon of light? Hence, that's the way we ended up with Planck's constant. Now, de Broglie did something similar. De Broglie said, well, then can't we have wave-like motion or apply wave mathematics to a particle? And we end up with the de Broglie equation when we do that. And honestly, I am not going to talk about that very much. If it's needed, that's going to be a formula that's on your chart. Chances of it being in there are pretty slim. But basically, what I want you to see is that as you increase the mass of a particle, as that gets bigger, you decrease the wavelength. Of course, now velocity comes in there too, so it's not a strict type of situation here. Often if you decrease the mass, you're decreasing the velocity and so forth. And I just don't talk about it any more than that. It's there. Now, I do want to go into Heisenberg and Max Born a little bit. This is often called the Heisenberg. I don't know how it got named after Heisenberg and not Born. We don't call it the Born uncertainty principle. You'll usually see it listed as the Heisenberg uncertainty principle. Now, effectively what he's saying is because of the tiny, subatomic or microscopic nature of an atom, it's impossible to know the exact position and the exact momentum. Mass times velocity is momentum. So in effect, we can't know the velocity with 100% certainty simultaneously. So that delta would give us an indication of kind of the plus or minus uncertainty with which we can measure that value. And so the degree of certainty of x times the degree in the momentum, in an ideal situation, it'd be 0. We'd know them both perfectly. But it's not. Instead, it's Planck's constant over, and boy, pi just seems to show up all over the place, divided by 4 pi. So what they're saying is that the product of those uncertainties is always going to be greater than or equal to. We're not going to be doing this mathematically. This is just an indicator. What that says is that any experiment that I perform to get at the velocity or momentum of the particle messes up the position and makes it so that I cannot know the position to any high degree of certainty, and vice versa. So if I know one very well, or the better I know one, the less I know about the other. More I know about one, the less I know about the other. And there's an old joke that says, Heisenberg, that's a German name, was driving on the Autobahn, and he was stopped by the police, and the officer came up to him and said, "Sir, do you know how fast you are going?" And Heisenberg looked up and said, "No, but I do know my position." Okay, that's a chemistry joke for you. Now, in the next video, what we want to do is focus on Schrodinger, and we're going to be looking at the solutions of Schrodinger's equation. So hold that thought. We'll be right back. For now, signing off.